go. And Tamas, please feel free to go ahead. Thanks.
Sure, Sam. Yeah, so thanks for organizing, Sam, and for having me here. Yeah, so like you said, recently joined Cosigns. I'm here till December, working with Paul Fernhead. This is work I recently finished with my PhD supervisor, Chris. It's about sort of designing couplings for unbiased MCMC that scale well with the dimension. I guess as a first example, you might think, let's look at the random walks as the theory sort of for single chain is well developed. So we essentially try to extend that to 2 chains. So like I said, the motivation is this unbiased MCMC with couplings paper by Pierre Jacob. And there they use this lag coupling construction. So roughly speaking, if you haven't seen this before, instead of sort of just your one chain X, which would be the black one here in this figure, you run a secondary chain Y, which is the red one here, and sort of continues up to here. You start them at the same points, and you run them sort of marginally with the same kernel. So every step of the X chain is sort of one step of random walk with fixed step size, and similarly for the Y chain, marginal. And the way you run them jointly is first you take L steps with your X chain. In this case, you take 100 steps, and then you start off the Y chain, and you update the chains jointly at each time step, such that they sort of get together as time goes on, and they eventually meet after a finite number of iterations. And what you can do with this construction is construct unbiased estimators for sort of expectations of the target. This is an example of one. The specific form of the estimate doesn't really matter. What you should think of is this figure here. You just sum up all the states of the X chain up to here, subtract off all the states of the Y chain. I guess, yeah, sum of all the states of the Y chain up to here, and you weight them appropriately. And this gives you an unbiased estimate that looks like this. And what you could also use this framework for is convergence estimation to bound strong metrics like TVD or 1 Wasserstein or even P Wasserstein. And for TVD, the bound sort of looks like this, and you can see the meeting time comes into play as such. Now, given the nature of the couplings I'm going to introduce, it's more the second bit that we're interested in. Yeah. And I guess you might be wondering, okay, I mean, these can't just sort of hold straight away. Obviously, you have to satisfy some kind of conditions on the meeting time. I mean, it could have horrible tails, but really all of this is valid under very weak conditions on the meeting time and function H. I mean, you can ask loads of questions about sort of when would this method perform well? I mean, I guess the obvious one is, how do you design a good coupling, forgetting about all the lag and the starting conditions, stuff like that. And in particular, what you'd want is the meeting times to essentially characterize the convergence of the algorithm well. So they should scale in proportion to the convergence of the underlying chain that starts from pi 0 and goes to pi, the target. What I'll focus on it here is dimensional scaling. And in particular, the random walk metropolis algorithm as a start to this. So it's the standard setup where the target's continuous, takes values in RD, proposal's just a Gaussian centered at the current state, with step size h or proposal variance h squared. And you do the standard draw uniform and accept it if the uniform falls under the metropolis Hastings ratio. And sort of here, the theory is all well developed. I mean, the product target limit of Gareth-Roberts says that you should scale the proposal as such, as L times d to the minus a half, where L is a constant. And that's sort of optimal both for the stationary phase and the transient phase, as they show in a later paper with Ola Christensen. And sort of the time to convergence is known to be order d. So really, we should aim for order d meeting times here. So let's just start straight away with kernel coupling. That does satisfy the regularity conditions that they impose in the unbiased MCMC paper. So for any sort of metropolis Hastings coupling, you could think of sort of generating it as first coupling proposals, and then separately decouple the acceptance steps. So for the proposal steps, here this so-called gamma coupling or maximal coupling with independent residuals. What you do is you first draw an X proposal, say somewhere around here, probably easier if I draw. We draw an X proposal here. Then, sorry, did you want to say something?
Oh yeah, thank you for drawing because I was getting confused. Thank you so much.
It's all right. Yeah, so you draw your X proposal here. You look at this height here and you draw uniformly on the height. If you land somewhere over here, then you make the proposals the same. So you just set yp equals xp, and if you land over here, then you sample the y proposal independently from this area 2 prime here. And you can kind of repeat the process you did with the x proposal here, as in you draw your y proposal, you draw a height, and if it lands somewhere over here, then you accept it, otherwise you reject it. And sort of this gives, I mean, you can kind of see how this sort of preserves the marginal distribution, so it's correct, at least pictorially.
As we're very few, can I ask you to explain again? If you sample XP where you sampled it, and then you sample a uniform between 0 and the blue curve, right?
Yeah.
And then if the uniform happens to fall between 0 and the orange curve?
Yes, you make the proposals the same.
Okay, but then if it falls above that, above the orange curve and below the blue curve, what do you do again?
You sample the y proposal. Okay, well, you rejection sample the y proposal such that, okay, you can think of sampling the y proposal as sampling uniformly under the curve, right? So you sample uniformly under the curve until you hit the area 2 prime here, and then you accept the point.
Okay, and 2 prime is the area in the right distribution above the blue curve.
Yes.
And okay, gotcha.
And beneath the orange curve.
Okay.
Yeah, so essentially what you do in the y proposal is if the steps are the same, then you sample it uniformly from the area 1. And so if the proposals are the same, you sample it uniformly from the area 1. And if they're different, you sample it uniformly from the area 2 prime. So that kind of together gives you a uniform sample under the curve for the y proposal. So it's correct in a way.
Okay, thank you.
That's right. So this gives you a positive chance of sort of proposing the same value, which is essentially what you want when you want to meet. And in fact, it gives you a maximal chance of proposing the same value. And you can kind of see this pictorially. It can't be higher than the area of overlap, the probability of proposing the same point. And ideally, you'd want to sort of also accept with highest probability if you propose the same point, and you can achieve that by using the same uniform to accept and reject in both chains. And sort of under weak conditions, as in you assume like a Lyapunov drift and all that stuff you use to prove convergence, if you use this coupling, then you can show that the meeting times have a geometric tail, and then sort of all the analysis carries through, and unbiased MCMC is valid. So that's sort of satisfying the necessary condition. It's sufficient to use this coupling. Yeah, but if you look at the dimensional scaling, sorry, I should probably delete. But if you look at how the meeting time scale with dimension, if you use this coupling, this is just a simulation, then you can see that the average meeting times, and in fact, the whole distribution of the meeting time scales exponentially with the dimension. So clearly it's not doing a great job as the increased dimension. And I'm really not trying hard to break it here. It's just standard Gaussians and increasing dimension, and I start the chains independently from the target. So clearly we need to do better. So let's have a closer look at what happens in high dimensions. So first off, sort of for any coupling of Metropolis Hastings kernels, it's clear that, to have the chains meet immediately from points X, start points X and Y, you need to propose the same point and also accept it. So the chance of meeting it at one iteration is upper bounded by the chance of proposing the same point. And now for any coupling of the random walk, chance of proposing the same point is upper bounded by this area of overlap here. And the previous coupling I showed you maximizes this, so this is an equality. And you can kind of see this in one dimension, is twice the tail of a Gaussian. Split it in half here. Sort of the correct, I guess, quantity to look at is this. And by just applying the standard Gaussian tail bound, you can upper bound it by this quantity here. Now, in high dimensions, what happens is that any local metropolis Hastings algorithm needs to make smaller and smaller moves. Yet at the same time, so the distance between points, if you sample them, say, independently from the target, grows. So you kind of have this double whammy here where the upper bit is order D, but the lower bit for the random walk is order 1 over D. So unless you manage to contract the chains so that they're order rate squared or order 1 over D apart from order D, then your chance of meeting is exponentially small at each iteration. So really what happens here is that basically up here, you just sample some independent chains that have a very tiny chance of meeting at each iteration. And it just so happens that sort of once in every 10,000 steps, I guess cumulatively, that probability is reasonable. So what we should do is, instead of trying to design couplings that at each iteration have a maximum chance of meeting, we should first design, we should first focus on contracting the chains down to order 1 over D, and then say swapping to something that allows for exact meeting. And this kind of shows up in a bunch of analyses of MCMC algorithm as well. The couplings geared towards TBD, like the maximal one I showed you before, don't scale well with dimension, as in they don't give you sort of geometric ergodicity with quantitative rates, just qualitative rates, whereas couplings that focus on contraction and are adapted towards something like the 1 Wasserstein distance, they actually give good rates. Right, so instead of trying to maximize chance of meeting, we'll optimize for contraction in squared Euclidean distance. And for that, it's helpful to write down the coupled random walk updates as such. It's just the current state plus Gaussian noise times the Bernoulli accept reject. And for simplicity, I'll restrict to the set of 2-stage kernel couplings. Basically, you just couple the noises first, and irrespectively of that, you couple the uniforms. Now, spoilers, what I'll just do is I'll just pick the uniforms the same. So really the trick is how you couple the noises. Okay, so the optimization problem is we'd like to find kernel coupling that minimizes the expectation, this expectation here. So basically you want to maximize contraction over 1 step. This doesn't look particularly nice, and it doesn't really tell you much about what you should be doing. So we'll need to massage this objective a bit. Sort of facts from optimal transport can be used to say that this is equivalent to maximizing this inner product here. It's sort of clear because you can just expand this as squared norm of x plus squared norm of y minus twice the inner product. Sort of squared norm of x that just depends on the marginal behavior of the x chain, doesn't depend on the joint. So instead, we're maximizing this inner product of all couplings on average. And further, we can expand this just using the random walk step decomposition I introduced before as such. Now, the important thing here is that this bit of the expression does not depend on the coupling because the first term is constant. The noise in the second term just depends on the x chain, and the noise in the third term just depends on the y chain. So really, an equivalent objective is to maximize the expectation of this expression here. So that's just the inner product of the noises times the product of the Bernoullis. So roughly speaking, you can think of as finding the coupling that tries to accept simultaneously while also making the proposal similar. And this is a bit better, but it's still not particularly helpful. It's not clear what you should be doing with the coupling. So to make progress here, and because we're interested in the high dimensional case, I'll take a closer look at the acceptance step in high dimensions. So writing the log density as V, and calling that the proposal is written like this, I'll do the standard thing people do in dimensional scaling literature and just Taylor expand the log acceptance ratio. So I guess the second order, this is the exact Taylor expansion with the Lagrange remainder. And you can see that you have an inner product term with the score and the noise, and there's this Hessian term here, which involves the quadratic form in the noise. And the key here is the third bit, where, you can just look at the log acceptance ratio as a rescaled sort of magnitude of the score times the projection of the noise onto the normalized gradient, plus the Hessian term. Now, as you take dimension to infinity with an appropriate scaling of the step size, then actually what happens is that this Hessian term goes to constant under sort of typical asymptotic settings. And you can clearly see this in the standard Gaussian target because sort of the square root of the Hessian is just constant matrix, it's the identity. So basically this is, I think it's L squared over 2 times a chi squared over D. So that just goes to L squared in L2 as dimension goes to infinity. So basically the key here is that all the noise in the log acceptance ratio in high dimensions comes from the uniform that you use to accept and reject, and the projection of the noise onto the normalized gradient. So in essence, it's all low dimensional, and this makes the problem tractable. Right, so using the intuition from before, I can write down that objective that we were interested in as approximately this. The only noise here is, I guess, the proposals in the inner product times the uniforms and the projections of the noises in the acceptance bit. Sorry, projections of the noises onto the normalized gradients in the acceptance bit. So these are the Z grads. So what you could think of doing here is sort of factorizing this. In the first bit, you should make the noises exactly the same to maximize the expectation of the first part, irrespective of the second part. And in that case, this expectation goes to constant as dimension goes to infinity. But also, it still goes to constant if you change a few of the coordinates in both of these. So in essence, this is sort of robust to low dimensional perturbations of the common random number coupling, where you just pick the same thing. And separately of this, if you try and maximize the expectation of the product of the acceptance Bernoullis, then a sensible thing to do is to pick the same uniform and pick the same projection of the noise onto the normalized gradient. And this is exactly optimal if these constants AX and AY are the same. So putting it all together, this suggests the so-called gradient common random number coupling, where to sample, I guess, to obtain the noises of the X and the Y chain, you start with the same standard Gaussian, but for the X chain in particular, you change the projection onto the normalized gradient to the same Gaussian that you use in the Y proposal. So basically, these are essentially pointing in the same direction, with the difference that the projections onto the respective normalized gradients are the same. And to sort of enforce that the chains accept at the same time, or to make them try accept at the same time, I'll pick the same uniforms in the acceptance steps. Yeah. And sort of by design, as it turns out, this gradient common random number coupling is asymptotically optimal for contraction among all the couplings that are on this sort of set of two-stage couplings. And that's basically, it's just directly a consequence of this derivation here. And you don't have to do this construction that I used here specifically. Essentially, any coupling where the projection of the noise onto the gradient matches up with the projection of the noise onto the gradient in the other chain, and sort of the noises are mostly the same in high dimensions, that this will still hold true. And the really important thing here is if the chains are marginally stationary, then this coupling is optimal over all Markovian couplings. So really, we're doing pretty well. And as it will turn out, I guess, from the analysis, that this is essentially necessary to get good behavior in high dimensions. Right, so I guess now we have a coupling that we derived heuristically, and it seems like it does a good job amongst the hopefully pretty large class of couplings in terms of contraction. So let's look at it numerically. So this is just experiments with high dimensional Gaussians, varying the eccentricity and the step size. I think the bottom bit, that would be the optimal scaling, I think. And here I used a different coupling. This is just to compare it. Something else, I'll talk about this a bit later. But basically, as you can see, that irrespective of the step size and the eccentricity, the step size scaling, I should say, it does pretty well. in terms of contracting the chains to essentially vanishingly close. So that's a good thing. Now it'd be nice to be able to justify this. So we looked at trying to analyze how this coupling behaves. And really these traces here look pretty smooth. Sorry. So that to us suggested that we might be able to show an ordinary differential equation limit as dimension goes to infinity. And so we looked at, I guess, results that had the papers that had this, and the specific one we found was this Christensen, Robertson, Rosenthal paper from 2005 in JRSSB, where for spherical Gaussian targets, they consider a marker process that essentially characterizes its transient behavior, and they show that this converges weakly to the solution of an ODE. And sort of proof is pretty straightforward. It's textbook. You just look at the infinitesimal generator. You show that it goes to the infinitesimal generator of an ODE, and then you just promote that to weak convergence of this process, the solution of an ODE. So we essentially just take the proof and extend it to a couple pairs of random walk chains. They're limited to standard Gaussian targets because you need to consider a finite dimensional marker process. It's pretty straightforward to extend it to elliptical targets that have particular regular structure, but we're somehow limited by the same problems that they have, making the analysis more general. So yeah, we'll only consider analysis for the standard for the Gaussian target. Right. So they consider one-dimensional process that looks like 1 over d times, I guess, norm of x squared, but sped up by a factor of d. By direct extension, we consider the same thing for the y chain, and also the squared distance between the x and y chain that's rescaled by 1 over d and sped up by a factor of d. And somehow you can think of first coordinate, that's the marginal behavior of the x chain, second one, that's the marginal behavior of the y chain, and the third one, that's the process we're interested in, it's sort of the joint behavior of the chain. And in the standard Gaussian case, this is marked up under the GCRN coupling that I introduced, and sort of by using the same proof method, it just falls through that this converges weakly to the solution of an ODE with an explicit drift that I didn't write down because it's ugly. And somehow, you know, that this completely characterizes how the coupled chains behave up to this rescaling of 1 over d. And somehow the ODE limit's nice because it sort of can characterize how the coupled chains behave from essentially any sort of starting points. So if you think of starting marginally from the stationary distribution, then this is 1 in high dimensions. This is also 1. And I guess if you sample the points independently, then this would be 2. And you just run your ODE with the starting conditions, and you look at how long it takes for this to basically go to 0. I guess one nice thing is that when both chains are marginally stationary, then yeah, first two coordinates are fixed, like I said. And you essentially just reduce an ODE for the squared distance, and it looks something like this, maybe with a factor of 2 in front of the expected squared jumping distance. And this is used as an efficiency metric for, I guess, Markov chains. And so sort of you can see that this goes down fastest to 0 if the expected square jumping distance is largest. So this directly shows that to, I guess, get the best contraction behavior with GCRN, you should scale the step size exactly as you would for, I guess, if you only ran one chain, wanted it to mix quickly. So basically,
one small question. So you know how with the pictures on the previous page, you see very smooth decay of the distance between them?
Yeah.
So I understand that the theoretical results only apply to the spherical Gaussian case, at least presently. But,
yes.
But qualitatively, if you run the same couplings for things that are non-Gaussian, say, or non-act, is it still quite smooth behavior you see, or is it somehow rougher?
Well, okay. Well, admittedly, I haven't tried too hard to break it. But you know, for like the stochastic volatility model example that I have, that is admittedly close to Gaussian, but it does have a
No,
third
sure.
derivative. Yeah, it's still very smooth.
Okay, great. Thanks.
But okay, right, skipping ahead. You know, even in finite dimension, you see these blips, where one chain accepts and one chain rejects them. They're sort of pulled apart. And yeah, you get this in for those things as well. But yeah, it all looks smooth. Somehow, if you look at the Taylor expansions of the log acceptance ratio, kind of the key thing here is that the Hessian term is basically constant in high dimension. So, you know, this I just looked at for Gaussians because the Hessian's constant. But, you know, you can equally think of this being kind of a product target with kind of bounded third derivative. And even then, that's basically constant in high dimension. So I would expect it to be smooth. But yeah, in terms of actually proving that sort of that helps with bounding convergence and stuff like that, I have no idea.
Sure. No, that's really helpful. Thanks.
No worries. Cool. So that's the ODE limit for this spherical case. So analysis process just reduces the analysis of ODE. Yeah, so to show you that, I guess I didn't mess up calculations. Here is, I guess, in dimension 2000, various starting conditions, various step sizes, how a trace of the square distance between chains matches up with the ODE limit. So that the ODE limit, that would be a dashed line. In this case, the coupling that's optimal for contraction over all Markovian couplings, not just a restricted set I considered, is also tractable, or at least its ODE limit is. And yeah, so I drew that with a dashed line that's in blue. And you can see that actually the ODE limits and the trace of the process sort of approaches that of the optimal Markovian one. So you don't lose out much by doing this optimization over the restricted set, which is nice. And sort of digging in deeper into how the ODE behaves, sort of long time behavior, we look at the unique stable fixed points of the ODE, and as these plots show, it does contract to zero. They're all starting conditions and step sizes. To look at how quickly it contracts, you look at the drift term. So that would be this one here. Obviously, optimize ESJD. So, sorry. Oh, no, sorry. That's for the step size. But yeah, you look at the drift term. And we find that it optimizes the drift point-wise amongst all couplings in the restricted set, which is nice. So you converge, I guess you contract the chain as quickly as possible. And yeah, for the step size scaling, you get the same one as the marginal chains, which is nice. Okay, well, that's sort of the spherical Gaussian case, which is probably less interesting. The analysis for the elliptical Gaussian case is a bit different. So we can get an ODE limit under very regular structure like this. It's because we need a finite dimensional marker process, and we get this here because you can sort of consider the triplets as we did before of x, y, and the difference between x and y for the, I guess, odd coordinates and the even coordinates. But that feels restrictive. So instead, we just consider these triplets here for sort of all integer k, or all positive k if you want. It's the same thing. And we basically just do direct calculations to get, I guess, results of the same nature as before. So long time behavior, you look at sort of a fixed point of all those equations. I guess, yeah, so fixed points, we're one step change in these things is zero, I should say. And you can basically look at the one step change in the square distance here. And for contraction, you'd want to, I guess, maximize the difference in that. So that essentially is an expression analogous to the drift term of the ODE in the standard Gaussian case. And you can work with that. And basically the same conclusions apply as in the spherical case. So it contracts to zero, it's quickest for contraction. Scale same with the step size as the marginal change there. So really the coupling seems to be insensitive to how eccentric the target is. And we can also do the analysis to other couplings in this elliptical case. We also consider the coupling that just uses the same noise in the proposal. And we also consider the so-called deflection coupling, where the proposals for both chains are essentially the same, except for the one coordinate in direction of the vector x minus y, where we flip the noise of the y chain versus the x chain. And again, looking at the fixed point equation, you get the long time behavior, and you can see that they fail for high dimensional elliptical targets. And GCRN does not. Okay, I mean, so I introduced the coupling that used gradient information to get great contraction in high dimension. Yes or no, this only applies to Gaussian targets, but I'll show you an experiment where it's not Gaussian and it still does well. But sort of introducing gradients into coupling of the random walk, the proposal doesn't have gradients, feels like cheating. So a natural question to ask is, can you get away with getting good contraction while not using gradients? And I would say probably not in high enough dimension. So for instance, if you use GCRN with approximate gradients, which as a proxy, I fixed here the correlation of the projections onto the gradients to be rho strictly less than 1 in all dimensions. Then again, the fixed point, you can do the ODE limit, and the fixed point of the ODE limit says that actually the square distance between chains is order D in high dimensions. So you essentially still have an exponentially small chance of meeting, so it doesn't do well. You need this correlation to go to 1 as dimension goes up. So basically you need the gradient approximation to be, or at least the direction of the gradient to be arbitrarily accurate as you go up in dimension. So yeah, you can't get away with approximate gradients. But if you can have, amazing preconditioning that basically reduces your target to spherical, then I guess it's kind of obvious that you can get away with not using gradients, because sort of the gradient is just, x minus a constant. Or I guess minus x plus a constant. And there you can use this reflection coupling, which is basically equivalent to GCRN when both chains are marginally stationary. And they proposed this in the unbiased MCMC paper, and they showed it works great on spherical Gaussian targets. But, if you use this coupling in the elliptical case, as I show here, it fails again because it doesn't contract low enough at high enough dimension. But I mean, you can do a bit better than this by just normalizing the vectors x and y, and you essentially recover GCRN because it's equivalent to GCRN even when the chains aren't marginally stationary. Cool. Right, so that was, I guess, heuristically introducing a coupling that should perform well for contraction even in high dimensions, analyzing the properties of squared distance under that coupling, I guess for a sequence of regular targets. Here's how to apply this in practice. So obviously you need to contract the chains and then also meet if you want to use this for, I guess, convergence quantification, because uses for unbiased MCMC seem questionable because you're using gradients. So you first contract with GCRN up to a particular threshold, and then you can use something like a reflection maximal coupling to allow exact meetings. I guess the key here is the maximal bit, which allows the chains to meet. And the ordinary differential equation limit suggests that if you pick your threshold appropriately, then your meeting time should scale linearly, maybe up to some log terms. Now, initially, I was tempted to choose this threshold as sort of 1 over D, because then the maximal bit in the reflection maximal coupling has a sensible chance of meeting at each iteration. But actually, it turns out that order 1, as dimension goes up, tends to give fastest meeting times in practice. And basically, the reflection bit here gives you sort of random walk-like behavior in the distance. And sort of this balances out the exponential decay in distance you get by GCRN and the random walk behavior that you get from this. But I mean, you can do smaller delta and it won't be much worse. I guess in practice, you might want to use some kind of optimize it over a grid or something. But yeah, so you can use this 2-scale coupling to, I guess, estimate convergence and bias, get these kind of upper bounds on TVD and Wasserstein. I'll obviously look at convergence of random walks. That's the, I guess, immediate thing you can do. I'll look at also the bias of a Laplace approximation, which I'll quantify by running one chain that targets what you're actually interested in, another chain that targets the Laplace approximation. I'll couple them by GCRN in the sense that the projection of the noise onto the gradient for the actual target in the X chain is the same as the projection of the noise onto the, I guess, approximate gradient for the Y chain. I guess the gradient of the Laplace approximation in this case. And since GCRN uses the gradients, maybe we should use it for some kind of position-dependent random walk that also, I guess, exploits gradients. And one example of that is the hop algorithm, which basically is a position-dependent random walk that uses a massive scaling in the gradient direction to jump between contours, and that's complemented by the hug algorithm and this hug and hop algorithm, where you essentially try and traverse contours by doing something that's similar to HMC and BPS. And so I'll only use one running example. It's just a standard stochastic volatility model without hyperparameters, which basically your prior is a highly correlated AR1, and it comes into the likelihood as such. So you end up with something that's non-Gaussian and quite eccentric. So it'll be difficult for the chain, for the standard random walk chain, which is kind of the point here. So first off, you can see that GCRN does well at quantifying the bias of the algorithm. Sort of contracts nicely, and the meeting times are sort of on par with what the Wasserstein distance convergence would say, which is nice. If you do a Laplace approximation for the stochastic volatility model, which also use, I'll also quantify its bias in a bit, then you can get an approximation of the curvature, and you can plug that into the fixed point equation for the ODE limits to rule out these two other couplings that I tried, common random number and the reflection one. And you can see that the MCMC traces closely follow the long time behavior predicted by this curvature approximation. And yeah, they both do a pretty terrible job. Yeah, for the Laplace approximation, again, given that the couplings didn't work well for convergence, you'd expect them to give rubbish bounds on the bias, and indeed they do. But GCRN does much better, and sort of plugging in this bound and doing some crude approximations, it tells you that you can get less than 10% relative error for the mean of the actual distribution from the Laplace approximation. So somehow the target isn't Gaussian, but it's sensibly approximated by a Gaussian. Yeah, and for hug and hop, their sort of GCRN is maybe less costly because you're already evaluating the gradient for the hop kernel. And you can get informative bounds on squared Wasserstein and TBD, and they show that it converges more than 2 orders magnitude quicker than the random walk, which is, I guess, completely unsurprising, given that they use so much more information about the target. Right, so I guess to sum up, by bridging the optimal scaling and coupled MCMC literature, we can design contractive couplings that scale well with the dimension, but you need the gradient direction to, I guess, get good dimensional scaling for the random walk. At least the theory and the experiment suggest that the gradient is sufficient, but yeah, it's something to keep in mind. One nice thing is that our theory also can quantify when other couplings fail in high dimensions. You can just look at the fixed point equation, and you can immediately rule out whether it's, I guess, worth doing unbiased MCMC with the random walk. Yeah, and I guess, yeah, unbiased MCMC with the random walk, bit questionable. If you already have gradients coming into the coupling, why would you include them in the proposal? So the natural thing to look at is, can we extend the theory to something that does use gradients, like null and HMC? And they're sort of carrying out the heuristic optimization I did before to optimize for contraction. It looks like you need a Hessian gradient product, which maybe isn't that bad because you can do it with, say, finite differences in order d time. But at the same time, you can just use the coupling that uses the same noise in both proposals and the same uniform to accept and reject, and it seems to work fine in high dimension. So maybe all of that isn't necessary. And I guess extending the theory also possible. There's a natural connection with the product target diffusion limit. I'm pretty sure that it's possible to show that GCRN is equivalent to common random number coupled Langevin diffusions when the chains are marginally stationary. But I guess to get a good view of the entire couple process, even when the chains are sort of approaching the target marginally, then yeah, we'd have to look at sort of this diffusion limit out of stationarity, and the theory seems significantly more involved there, but might be extendable to our setting. Yes, I think that's right about what I wanted to say. Thanks for paying attention.